Hello friends, I welcome you in lecture number 4 on wave equation. In this lecture also we will discuss one question on the solution of one-dimensional wave equation which was asked in GTU Summer 2022 exam. The question is, find the deflection uxt of the vibrating string of length pi and ends fixed corresponding to 0 velocity and initial deflection given by fx equal to k times sin x minus sin 2x. We have discussed this type of problems in earlier lectures, and we know that to solve this type of problems we should remember the solution of one-dimensional wave equation which we have derived in lecture number 1 using method of separation of variables, and we know that the deflection uxt of vibrating string is given by sigma n equal to 1 to infinity bn cos lambda nt plus bn star sin lambda nt multiplied with sin n pi x divided by L, where L is the length of the vibrating string, and this solution is satisfying the boundary conditions u0t equal to ult equal to 0 for all values of time t, and also initial conditions ux0 equal to fx and del u by del t at x comma 0 is gx, and this bn and bn star are obtained by the formulas. Bn is obtained using this initial deflection fx. It is 2 by L integral from 0 to L fx multiplied with sin n pi x by L integral with respect to x, and bn star is given by 2 divided by c times n times pi integral 0 to L. Here we are using this initial velocity given by gx multiplied with sin n pi x by L integral with respect to x. In bn we are using value of initial deflection fx. In bn star we are using value of initial velocity which is gx, and this term is common, sin n pi x by L, in these three equations. Here we are writing cos lambda nt sin lambda nt, where lambda n are eigenvalues given by c n pi divided by L. So we should keep in mind all these things, and using this we are able to decide the deflection of vibrating string of given length and with given boundary and initial conditions. Here it is given that length of the string is L equal to pi, and it is given that ends are fixed. So we have boundary conditions that at x equal to 0 deflection is 0, and at x equal to pi deflection is also 0. That is, two ends are fixed at x equal to 0 and at x equal to pi, and it is given that velocity is 0 and initial deflection is fx equal to k times sin x minus sin 2x. That is, ux0 equal to fx is given by k times sin x minus sin 2x, and initial velocity is 0. That is, del u by del t at x comma 0 is given by gx equal to 0, and this is true for all values of x in the interval 0 to pi, because length of the string is pi, and these two conditions are true for all values of t which are non-negative. And here this is the problem of solution of one-dimensional wave equation. So we know that the solution of wave equation given by del square u by del t square equal to c square times del square u by del x square, satisfying the conditions. These are boundary conditions. These two are boundary conditions. We give them number 1, and these two are initial conditions. We give them number 2. So satisfying boundary conditions written in equation 1 and initial conditions written in equation 2 is uxt equal to sigma n equal to 1 to infinity bn cosine lambda n t plus bn star sin lambda n t multiplied with sin n pi x divided by L, where we have to determine this lambda n, bn and bn star. Lambda n is given by cn pi divided by L. Here length of the string is pi, so if we put L equal to pi, we have lambda n equal to c times n equal to 1 to 3 and so on. Similarly, we can determine bn using the formula 2 divided by L integral from 0 to L fx multiplied with sin n pi x divided by L integral with respect to x. Therefore, bn equal to 2 divided by L, length of the string is L equal to pi, so we substitute L equal to pi here, 0 to pi. Fx is initial deflection given by k times sin x minus sin 2x. So here we write k times sin x minus sin 2x, and here if I take L equal to pi, I will have sin n into x integral with respect to x, and I can take this k outside, that is independent of x, and I am taking these two inside the integration that I will require, and here I am multiplying this bracket by sin nx, and I am writing in this way 2 times sin nx into sin x minus sin nx into sin 2x integral with respect to x. This is equal to k divided by pi, and this I can again rewrite as integral from 0 to pi. 2 is multiplied with both of these two terms, that is 2 sin nx into sin x integral with respect to x, and I am separating. I multiply by k by pi, this term is multiplied by k by pi into 2, same thing for this, and I am taking negative sign outside the integral, 0 to pi 2 times sin nx times sin 2x integral with respect to x. Now to integrate this, first I have to use the formula that if I have minus 2 sin alpha into sin beta, then this I can rewrite as cosine of alpha plus beta minus cosine of alpha minus beta. So I can adjust that minus sign here. I can rewrite this as, here I am writing minus 2, and that I adjust with this one, I multiply with negative sign, and this I can rewrite by taking negative sign inside the bracket so that I can use this formula. Now I am using this formula. This is k by pi as it is integral from 0 to pi, and here I have minus 2 ss with alpha equal to nx, beta equal to x. Therefore, this is going to be cosine of nx plus x, and I can take x common, and I can directly write cosine of n plus 1x. Similarly, minus alpha minus beta, that is nx minus x, and if we take x common, it is n minus 1 into x. So, using this formula here, I am able to rewrite this as a subtraction of two cosine functions. Same thing I will do here, plus k by pi integral from 0 to pi. Here alpha is nx, beta is 2x. So this is going to be cosine of nx plus 2x, and if we take x common, we have cosine of n plus 2x, and here we have cosine of n minus 2x integral with respect to x. Now this is easy to integrate, k divided by pi as it is. Integral of cosine n plus 1x is sine of n plus 1 times x divided by coefficient of x, which is n plus 1. Same thing here, sine of n minus 1x divided by coefficient of n minus 1, and limits of x are from 0 to pi. Similarly, for second term, k divided by pi, integral of cosine of n plus 2x is going to be sine of n plus 2x divided by coefficient of x, which is n plus 2, minus sine of n minus 2x divided by n minus 2, and limits are from x equal to 0 to x equal to pi, and this is for Bn. Now we know that in Bn, n is taking the values 1, 2, 3 and so on. Now if you observe these two terms, then here I have n minus 1 in the denominator, and here I have n minus 2 in the denominator. So this will be undefined for n equal to 1, and this is not valid for n equal to 2. So this is valid if n is different from 1 and 2. This is valid if n is not equal to 1, n is not equal to 2, and for rest of the integers, positive integers, it is valid. So that we have to be careful that n is taking the values, n is taking all the natural numbers, but because I have n minus 1 in the denominator here, this is not valid for n equal to 1, and this is not valid for n equal to 2. Therefore, this expression for Bn is valid if n is different from 1 and 2. So we will calculate for n equal to 1 and n equal to 2, that is, we will calculate B1 and B2 separately, because this is undefined for n equal to 1 and n equal to 2. Now for rest of the integers, I can take upper limit and lower limit. Suppose I take x equal to pi here, I will have sine of n plus 1 into pi here, and n is natural number, so n plus 1 is also natural number, and we know that if I have multiple of pi which is positive integer or integer, then this is always 0. Integer multiple of pi is there, then sine has 0 value. So because n is positive integer, n plus 1 is also a positive integer, therefore this is going to be 0. Same thing here, sine n minus 1 into pi, that is also going to be 0. Same thing for n plus 2 into pi, this is also natural number, so n plus 2 pi is also a natural number, and same thing for here. So when x equal to pi, all these will become 0. Now for lower limit, if we take x equal to 0, I will get sine 0 here, same thing here in all these terms. So Bn will become 0 for all values of n except n equal to 1 and n equal to 2. So now I am writing that therefore Bn equal to 0 for all n belongs to n where n is different from 1, n is not equal to 1 and n is not equal to 2. And here we have used the fact that if I have sin n pi, then it is always 0 whenever this multiple of pi is an integer. And in our case, this n takes only positive integer values. So if n is positive integer, n plus 1 is also positive integer, n minus 1 is also an integer. All these will become integer, and whenever I have integer multiple of pi, and if I am taking sign of that integer multiple, that is always 0. Now we have to find out b1 and b2 separately. So for that we can start from this term. Suppose I want to start from this step, or I can start, okay, I can use this step, that if I am taking, suppose I give this number 1, I am writing Bn equal to in this form, and suppose I consider n equal to 1, suppose I am calculating B1, then this is going to be sin x, here also I will have sin x, so this will be sin square x, and here I will have sin x into sin 2x. So for that I will use that formula minus 2ss, and here I will not write this minus 1 and minus 2 because I will have 2 sin square x here. So now I am taking n equal to 1 in equation number 1 to find out b1. Taking n equal to 1 in equation number 1, we will have b suffix 1 equal to k divided by pi integral from 0 to pi 2 times sin square x integral with respect to x. I am taking n equal to 1 here, so I have sin x into sin x, that is sin square x, and minus 1 into minus 2 I am writing as 2 sin square x. And here I am taking n equal to 1, so that I will have sin x into sin 2x into minus 2. So I will keep minus 2 as it is. Here I will use this formula minus 2ss. So this I will write as minus 2 sin 2x into sin x into k divided by pi. So plus k divided by pi integral from 0 to pi, and here I am writing minus 2 sin 2x into sin x. I am taking n equal to 1, so this is for n equal to 1, and I already have sin 2x in the product. Let me check again. Sin 2x for n equal to 1, this is sin x and into minus 2. Now to integrate this, I am using the formula that if I have sin square alpha, then this I can rewrite as 1 minus cosine of 2 alpha divided by 2. That means 2 sin square alpha is 1 minus cos 2 alpha. So this I can rewrite as 1 minus cos 2x. So in the next step, therefore b1 equal to k divided by pi integral from 0 to pi 2 sin square x I am replacing by 1 minus cosine of 2x, and here I am applying that formula minus 2ss is c minus c, that is cosine of 2x plus x, that is 3x, minus cosine of 2x minus x, that is cos x, minus 2 sin alpha sin beta equal to cosine of alpha plus beta minus cosine of alpha minus beta integral with respect to x. Therefore b1 becomes k divided by pi integral of 1 with respect to x is x integral of sin 2x cos 2x is sin 2x divided by 2. Limits are for x equal to 0 to pi plus k divided by pi. Integral of cosine 3x is sin 3x divided by 3. Integral of cos x is sin x. Limits are from x equal to 0 to x equal to pi. And suppose for the first bracket, if I take x equal to pi, then I will have pi minus sin 2 pi divided by 2, but sin 2 pi is 0. And for lower limit it will be 0. When x equal to 0, this is 0, sin 0 is 0, plus k by pi. If I take x equal to pi, here I have sin 3 pi and here I have sin pi, and both are integral multiples of pi, so sin of integral multiple of pi is 0. For x equal to 0, we have sin 0 minus sin 0, that is 0. So therefore b1 is k divided by pi into pi, that is k. So value of b1 is k. Now I have to decide what is b2. So for that I am taking n equal to 2 in number 1, and let's see what we obtain for n equal to 2. b2 equal to k by pi is there, and if I take n equal to 2 here, I will have sin 2x into sin x, and so I will write minus 2 sin 2x into sin x. I will keep this minus 1 as it is. So minus 1 and minus 2 into sin 2x into sin x. So here I am writing minus 1 outside the bracket, integral of minus 2 times sin 2x into sin x integral with respect to x. And second part is, if I take n equal to 2 here, I will have minus 2 sin 2x into sin 2x, that is sin square 2x into minus 2. Now I will not require minus sign here, so that I will take outside. I will write this as minus k by pi 2 sin square 2x. So here I am writing minus k by pi integral from 0 to pi 2 times sin square 2x integral with respect to x. Here I will use that formula, minus 2 SS is c minus c. So cosine of 2x plus x, that is 3x, and minus cosine of 2x minus x, that is cos x. Therefore b2 equal to, and I have negative sign outside the integral, and 0 to pi cosine of 3x minus cosine of x integral with respect to x. I have written for this, and this I will rewrite as 1 minus cosine of double of this angle, that is 4x. So minus k by pi 1 minus 4x minus k divided by pi integral from 0 to pi 1 minus 2 sin square 2x is 1 minus cosine of 4x, 1 minus cos 4x integral with respect to x. Now integral of this is sin 3x by 3 minus sin x. Therefore b2 is minus k divided by pi integral of cos 3x is sin 3x by 3 integral of cos x is sin x integral from 0 to pi. And for the second part, integral is integral of 1 is x, integral of cos 4x is sin 4x divided by 4 integral from 0 to pi. Now if I take x equal to pi, here I will have sin 3 pi, this is sin pi, so that will be 0 for x equal to pi. And for x equal to 0 also I will have sin 0, here also sin 0, So this part will be 0. And if I take x equal to pi in this second bracket here, I will have pi minus sine 4 pi, that is 0, and for x equal to 0 I will have 0 minus sine 0, and this is minus k. So what we obtain, we find that value of b2 is minus k, and b1 we have obtained, that is b1 equal to k. So once we obtain this b1 and b2, now we can write down the deflection of string which is required. Therefore deflection uxt of the string is, we have written the formula, and we have this bn star. We have not written for bn star. This is for bn. Bn star is 2 divided by cn pi integral from 0 to L gx sin n pi x by L integral with respect to x. But gx is 0. Therefore I have to write bn star equal to 0 for n equal to 1, 2, 3 and so on. So this also we have to mention. We know that bn star is 0, but we have to write this step also. Now deflection is given by sigma n equal to 1 to infinity bn cosine of lambda t plus bn star sin lambda n t, but bn star is 0 for all n, so I am not writing it, and this is in the product sin n pi x divided by L. And what is L? L is pi here, and lambda n is c into n. So we are writing cosine of c into n into t into sin n x. Lambda n was cn pi over L, and L is pi, so lambda n is cn, that we are writing here. And if I take L equal to pi here, I will have sin nx. But we have value of bn non-zero for n equal to 1 and 2 only. So now I am writing in this way. For n equal to 1, this becomes b1 cos ct into sin x. For n equal to 2, it is b2 cosine of 2 times ct into sin 2x. And we have obtained that value of b1 is k and b2 is minus k. So that we substitute here. b1 is k cos ct sin x, b2 is minus k. So here I write minus k 2ct sin 2x, and if we wish we can write k in the k common, and we can write in the bracket cosine ct sin x minus cosine of 2ct into sin 2x. This is the required deflection of the string which satisfies given initial and boundary conditions. So this we have to obtain, and that we obtain using the formula for the solution of one-dimensional wave equation, which we have derived in lecture number 1 using the method of separation of variables. The new thing is here we have to be careful that because I have n minus 1 and n minus 2 in the denominator, I have to calculate b1 and b2 separately, and other constants bn becomes 0, and for b1 and b2 we have calculated separately, and then we substitute them into the expression for the solution of wave equation, and we derived the required deflection for the given problem. So in this way we can easily answer this type of problems, provided we should remember this formula for the solution of wave equation satisfying this boundary and initial conditions. So always remember that solution of this wave equation in this form satisfying those boundary and initial conditions is given by this formula, and where this lambda n, bn and bn star are given by respective formulas. So this is all about this session. I hope you like it. Thanks for watching.